Hi Math 215 students. In this video we're going to introduce linearly independent sets of vectors. This will go with section 1.7 and it will be the first of two videos for this section. Our outcomes for this video are as shown here. There are a couple new terms you'll want to be able to define, and then you'll want to be able to apply those terms and answer some questions related to them. So here is our first key definition. We're going to be talking about sets of vectors in this section, and one thing that we most often want to talk about when we talk about sets of vectors is linear independence. And so what that means is this: if we have a collection of n different vectors, which we'll call v1 through vn, we'll say that that set of vectors is linearly independent if the vector equation x1 v1 plus x2 v2 plus ... plus xn vn equals 0 has only one solution. Now, as you take a look at this vector equation, the things that are unknown are these coefficients, x1 through xn, and the question is there a way to choose coefficients to assign to these in order to make the zero vector? And if that was the only question, the answer would be yes, because we can obviously just let each coefficient be 0, and that would give us the trivial solution. But what we're interested in for linear independence is whether there's more than just the trivial solution. Is there a way to choose coefficients that are not all 0, that allow you to take those vectors v1 through vn and use them to produce the zero vector? Now, if on the other hand, there actually are numbers c1 through cn that are not all 0, but that do allow you to scale these vectors and add them together in such a way that you create the zero vector, then we'll say that the set is linearly dependent. So it all has to do with this equation and whether or not there is a non-trivial solution for the choice of those coefficients. Now, this is a key definition, so please do your best to remember the definition. Keep this equation firmly in mind. It will be showing up in many different places. And also, while you're at it, remember that the way we have defined linear independence or linear dependence is in terms of sets or collections of vectors. It's not correct to say that a vector is linearly independent or linearly dependent. You can only say the words linearly independent or linearly dependent correctly if you're talking about a set or a collection of vectors. All right, now let's see this in action. We've got here a collection of 3 different vectors, and we want to ask, are these vectors as a collection, are they linearly independent? Vectors 5, 0, 0, 7, 2, negative 6, and 9, 4, and negative 8. All right, so now how do we decide this? Well, we remember our definition. Remember, our definition says that they'll be linearly independent if the only way to attach coefficients to them to make the zero vector is to put zeros everywhere. So we're going to check that. We're going to see, is there a choice of coefficients that would make this expression equal to the zero vector? Now, this vector equation, we know how to solve those. We solve those usually by setting up an augmented matrix, and so we'll do that here. We'll take each of these vectors and write it as a column vector in the matrix, and for the augmented matrix, we'll take the zero vector and we'll write 0, 0, 0 down the right-hand side. Now, if we do some standard row reductions, taking 3 times the second row and adding it to the third row, for instance, you'll see that we do get a pivot position in each of those rows, and that pivot position happens before the column of zeros. So if we were to go ahead all the way to the reduced echelon form, we would see 1s on the main diagonal, and that would tell us that x1, our first variable, has to equal 0. x2 has to equal 0 as well, and x3 also has to equal 0. And that is the only solution. So because that is the only solution to this vector equation, and it is the solution where every variable is set equal to 0, we say that yes, the set is linearly independent. Again, we're just looking exactly at this definition. If there's only one solution, which must inevitably be the trivial solution, which is the case here, there's only one solution, then yes, the set is linearly independent. All right, let's take a look at a second example. Let's ask whether this collection of 3 vectors is linearly independent. And we'll start off the same way. We'll see if the vector equation has a solution other than the 0 solution. So we'll put each of those vectors as a column in our matrix, and we'll put 0 down the right-hand side for the augmented matrix. And now if you take 2 times row 3 and add it to row 2, you'll get a 0 in that spot there. And then if we take row 1 and we scale it to make the 0 appear in that bottommost position, you'll notice now that the second and third rows have a very, very similar format. In fact, it's probably not hard to imagine that if you were to scale the 18 correctly down to a -10, then they would completely wipe out the bottom row. And so we'll skip the showing the further steps, but this is the reduced echelon form you end up with. Now the question was, what can we say about these coefficients? And we can see that x1 plus 3x3 is equal to 0, so x1 is equal to minus 3x3. Similarly, x2 is equal to positive 1x3, and x3 is a free variable. So we end up with a solution. If we write it in parametric vector form, we'll see negative 3x3, 1x3, and x3 are our values for x1, x2, x3. And x3 is a free variable, so actually any multiple of this collection of values gives us a solution. And that means that there are many, many, many choices of x1, x2, x3 that allow you to produce the 0 vector. And since there are multiple solutions, we say that no, the set is not linearly independent. Instead, it's linearly dependent. All right, now in passing, what we just got done saying was that there was a solution, x3 times the vector negative 3, 1, 1, where x3 is a free variable. If we wanted to, what we could do is put these coefficients back in for x1, x2, and x3. We do have to choose what x3 is, but if we just chose a specific value like x3 equals 1, that would tell us that x1 is negative 3, x2 is 1, and x3 is 1. And plugging that in, you can verify that yes, indeed, negative 3 times this vector plus that vector plus that vector does equal the 0 vector. You'll see in the first entry, negative 3 plus 3 plus 0 equals 0. Negative 12 plus 10 plus 2 is equal to 0 in the second row. And positive 6 plus 4 minus 10 is equal to 0 as well. Now, when you do this, when you choose values for your free variables and you actually come up with numbers that work in the linear, in the equation that we're supposed to check, this is known as a linear dependence relation. And you'll notice that it gives a clear reason why our set is linearly dependent. The question was, are there non-zero coefficients you can use? And yes, indeed, there are. All right, so if you are ever asked for a linear dependence relation, what you'll want to do is just what we did in the previous slide. You'll want to row reduce the augmented matrix and actually come up with an answer defined in terms of your free variables. And then if you choose a value for your free variable, that will tell you what all of the variables should equal, and just use those numbers as coefficients for your linear dependence relation. Okay, now here's another question, third example. Are the columns of that matrix linearly independent? And so we'll do what we've done a couple times now. We're going to check to see if we can find coefficients that make this equation work, coefficients other than 0. And as we row reduce, we end up with a reduced echelon form that looks like this. And so the question is, what are these coefficients? And this tells us that x1 has to be 0 and x2 has to be 0. And we have a non-needed third row of zeros there. It doesn't really tell us anything. But because x1 and x2 are both 0, we do know that only the trivial solution works here. So yes, these columns are linearly independent. Now, one thing you'll notice is that we took our vectors to be columns of a matrix. And we've done things like that before, so that shouldn't be too much of a stretch. But one thing we can say then is that for any matrix A, the equation AX equals 0, which is a matrix form of this vector equation, has only the trivial solution exactly when the columns of A are linearly independent. All right? Now hopefully you can see the connection there. The solution AX equals 0 is pretty much the equation that goes with this augmented matrix, but this vector equation testing for linear independence also goes with this augmented matrix. They're basically the same question, and that's why the theorem is true. Okay, now as we decide whether sets of vectors are linearly independent or dependent, there are a couple shortcuts that can help us to decide in some cases. Now I'll warn you up front that these shortcuts work only in the cases that we're going to talk about. They can't help you decide whether every set is linear dependent or independent. But let's see what we start with. Our first rule is this. If your set of vectors includes the 0 vector, then that set is guaranteed to be linearly dependent. Okay? Now, we're actually going to go through the proof. It's not so complicated. The idea is just if your first vector were the 0 vector, and you wanted to test whether this was linearly independent or not, you would just see, can I choose coefficients to make the 0 vector? And I can, actually. I can take 1 as my first coefficient, and 0 as all the other coefficients. But the point was, I did have a non-zero number as a coefficient, so that is a non-trivial solution to this equation, and that guarantees that this set is linearly dependent. Okay? All right, so at a glance, if you see the vector 0, you know automatically that the set is linearly dependent. The next shortcut rule is what I'm going to call the single vector rule, and it says that if a set of vectors just includes one vector, let's call that vector v, and as long as v is not the 0 vector, then that set of one vector is guaranteed to be linearly independent. So, how do we prove that? Well, the idea is if you have a single vector and you want to know how to make the 0 vector out of that, the only thing you can scale by and accomplish that is 0, as long as v is something that is not the 0 vector. Now, because x1 has to equal 0 then, we get the linear independence that we're looking for. Okay, so as we take a quick look at some examples here, we check, is this first set of vectors linearly independent or dependent? Is the second set linearly independent or dependent? And notice that it's a set that contains just one vector. And what about the third set? If you'd like, feel free to go ahead and pause the video. We'll come back in a couple seconds. All right, now in the first example, we have a set of vectors, and one thing that's notable here is that the 0 vector is included in them, the 0 vector of R2. And since the 0 vector always makes a set of vectors linearly dependent, we know that this is a linearly dependent set. Okay, for these next two examples, we have sets of vectors that just have a single vector in them. And so the rule says that if that vector is not the 0 vector, then the set is linearly independent. So that's the case here. On the other hand, if the single vector in your set is the 0 vector, then we default back to the 0 vector rule, and we find that this last set is linearly dependent. Okay, now there are a couple other shortcuts. One deals with having exactly 2 vectors. If in a set of exactly 2 vectors, neither vector is a multiple of the other, then the set is guaranteed to be linearly independent. If, on the other hand, one of them is a multiple of the other, then the set is linearly dependent. Okay, so let's suppose that you had 2 vectors, v1 and v2, and suppose that v2 was a scalar multiple of V1. In other words, V2 is a multiple of V1, and C is a constant there. What we can do is we can write C times V1 plus minus 1 times V2 is equal to 0. And since minus 1 is definitely not 0, this is a non-trivial way of choosing those coefficients, so we're guaranteed to have a linearly dependent set. Now, on the other hand, if neither of these was a multiple of the other, there's just no way of choosing coefficients to make the 0 vector out. If you found such a way, you would be able to move things around and show that actually one of those vectors was a multiple of the other. So if they're not multiples of each other, then the set is guaranteed to be linearly independent. Okay, now, finally there's the too many for the size rule. If a set of vectors from Rn contains more than n vectors, then the set is guaranteed to be linearly dependent. Now notice that n tells us how many entries are in the vector, and if there are more vectors than there are entries in the vectors, then the set is guaranteed to be linearly dependent. Again, the reason why is pretty simple. Suppose that you took those vectors and you made a matrix A having them as its columns. And if you set up the augmented matrix with zeros and you row reduced, you're going to find that because these vectors are from Rn, your matrix has n rows, so only n pivot positions are possible. On the other hand, you have more than n columns coming before the last one, so we're guaranteed to have a free variable when we solve that equation. And of course, if we have a free variable, then there's more than one solution to this equation, and that means that we're guaranteed to have a linearly dependent set. All right, so let's take a look at a couple more examples. Taking a look at the two vectors rule, that certainly applies to these latter two, and the too many for the size rule works in the first case because you'll notice that these vectors are from R2. There are only 2 entries, but there are 3 vectors. So there are more vectors than entries in the vector, and that's the rule we just talked about. So that last rule tells us that this first example is guaranteed to be linearly dependent. Now, for the first of those rules, the two vectors rule, we're going to take a look to see if either of these vectors is a multiple of the other. Now, if I were to take this second vector and multiply by 3, I'd get a 6 and I'd get a 3, but then I'd need a 0. And similarly, if you were to multiply by a third, you'll see that there's nothing really that works to show that one of these is a multiple of the other. Neither of these is a multiple of the other, so we're guaranteed that this set is linearly independent. Now in the last example here, 3, 9, negative 15, negative 4, negative 12, 20, you may start to suspect things, given that these are all multiples of 3 and these are all multiples of 4. And in fact, if you were to multiply this first vector by negative 4/3, 3 times negative 4/3 is minus 4, 9 times negative 4/3 is minus 12, and minus 15 times negative 4/3 is positive 20. So there definitely is a relationship. The second vector is a multiple of the first one, and that guarantees that this set of two vectors is linearly dependent. Okay, now we've talked about 4 shortcuts in the last couple slides that allow you to determine quickly if a set of vectors is linearly independent. Now, let's ask this question. If we have the matrix with the columns shown here, are the columns linearly independent? And can we use a shortcut? Well, if we think about our shortcuts, the 0 vector shortcut doesn't apply here because none of these vectors is a 0 vector. We have more than one vector or 2 vectors, so we can't really use those rules because they applied only to the situation where you had just one vector in your set or 2 vectors in your set. And finally, there are 4 entries in these vectors, but there are only 3 vectors. There are not more vectors than entries. And because of that, we know that none of the shortcuts we've talked about applies here. We do not know at this moment whether the columns are linearly independent or not. The way to decide that is to just go back to basics. Remember, our original definition was just is there more than one solution to ax equals 0? If we set up the augmented matrix with a column of zeros at the end, and if we do all of the row reduction, the reduced echelon form looks like this. And hopefully that allows you to see that each coefficient would have to be equal to 0, and there is only one answer. So, because there's only one answer to ax equals 0, are the columns linearly independent? And the answer is yes, they are. Okay, so we're going to wrap up here really quickly. There's a useful connection that kind of connects the idea of linear independence or dependence with linear combinations. So we're going to say that a set of two or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. Okay. In other words, that set is linearly dependent exactly when one of the vectors is a linear combination of the others. Now, if we take a look at these examples, these are the linearly dependent sets from our earlier slides. You'll see that 0 as a vector is a linear combination of 5, 1, and 2, 7. If you take 0 times 5, 1 plus 0 times 2, 7, you end up getting the 0 vector. So the linear combination certainly appears there. This is another linearly dependent set. It's got more vectors than entries. And we have not shown it yet, but if you were to check whether 5, 6 is a linear combination of 1, 2, and 3, 4, you'll find that the answer is yes. There is a way of scaling these vectors in order to produce that one. And because this second vector is a multiple of the first one, there is clearly a linear combination. We said negative 4/3 times that first vector, which is a linear combination, is equal to this second vector. All right? Well, in the next video, we're going to expand upon this line a little bit, and we're going to talk a little bit about why you might care about linearly dependent or independent sets. But for right now, we'll just wrap up here. Please review these outcomes and make sure that you can answer each of these. If you have any questions, let me know, and I will see you at the next video.